Hello, I'm going to work through each of these problems on the study guide for the quiz on Thursday. And that quiz is going to be over finding the area of figures and parallelograms. So, this first section is about finding the area of different shaped figures. And there's three methods that we're going to focus on. There's lots of different methods, and on Thursday's quiz, there's not a particular method students need to know. They need to simply be able to solve the problem. But exposure to different strategies is always a good thing. So, example A here is going to be solved using a strategy that involves decomposing the larger figure into two smaller shapes, finding the areas of those smaller shapes, and then adding those areas back together to find the area of the entire figure. There's different places a student may choose to decompose this figure. I'm going to choose to decompose along this blue line so that I have a smaller rectangle on the left and a larger rectangle on the right. If I can find the side lengths of these rectangles, I can then multiply the side lengths to find the area. So the smaller rectangle has a side length of 3 and 2. When you multiply those together, you find an area of 6 square units. Focusing on the larger rectangle, it has a side length of 3 and the other side length is 6. So when we multiply the side lengths, we find an area of 18 square units. And then we're going to add the separate areas of the smaller figures together to find the area of the total figure, or the total area for the figure, which would be 24 square units. Example B here is taking advantage of a strategy where you decompose it into two smaller figures and then rearrange them, putting them together into a shape that you can find the area of. So I'm going to decompose down the middle here so that I have two right triangles, and I can take either triangle and move it to pair up with the other, making a rectangle that we can then find the area of. So if I decide to move this rectangle that way, you can see I can line it up with the other triangle, and then now we have a rectangle that we can find the area of. This rectangle has side lengths of 3 and 4. When we multiply those, we find an area of 12 square units for this purple shape. Okay, example C shows a large figure that has been, that has a hole or open space in it. And the way we're going to find the area for this figure is to imagine that this area is filled in. Notice that both sides have a side length of 6. When we multiply those, we get an area of 36 square units. And then remembering that we actually don't have those two pieces, we subtract those 2 square units from the 36, which gives us an area of 34 square units. So after those first 3 questions, there's 3 more questions that represent the 3 strategies, but these are a bit more difficult. So looking at the larger figure, the key here is to decompose the figure into multiple smaller rectangles, find the area of the rectangles, and then add them back together to find the area of the whole shape. Again, there's multiple areas where a student may choose to decompose. This is simply one of them. I'm going to find the area of each one of these rectangles and then add them up. So this rectangle all the way to the left has a side length of 3 and a side length of 5. So when we multiply those side lengths, we get an area of 15 square units. Moving to the rectangle in the middle, we can see we have a side length of 3. And I do want to comment that this 1 does not refer to this side. It applies to this side here, this tiny little length right there. Okay, so this middle rectangle has a side length of 3. We need to know what this side would be. And we can figure this out a couple different ways. One is noticing that this rectangle has a side length of 3. Opposite sides in a rectangle are the same. So that means this side is also 3. And so if this distance is 3 and this distance is 2, that means we have a side length of 5. So we have a side length of 3, side length of 5. That's an area of 15 square units. And we finally have a rectangle with the side lengths plainly marked, 2 and 6. Multiply those side lengths together for an area of 12 square units. And we want to add those 3 areas together because we want to find the area of the whole figure. We know 15 plus 15 is 30, plus 12, 42. So the area for the whole figure is 42 square units. All right, we have a small little rectangle here, and it has an opening or a gap. But we're going to temporarily imagine that it's filled in. And if we do so, then the area of that rectangle is the side length 5 centimeters multiplied by the side length 8 centimeters for an area of 40. And then we remember that there's a piece missing from the rectangle, and that piece has an area of 2 centimeters multiplied by 3 centimeters, which is 6 centimeters. We want to subtract that from the 40 centimeters. So we don't want to add it to the 40 because we know that we're starting out with less than that rectangle, and 40 square centimeters is the area of that rectangle if it were all the way filled in, which it's not. So we're going to take that 6 square centimeters from the 40 square centimeters to leave us with an area for the shaded region of 34 square centimeters. This question here with the purple looks like a purple square that's surrounding a square hole or opening. Or maybe you see right off the bat that there's 4 right triangles. One way to solve this problem, and probably the recommended way, is to move or rearrange these triangles so that you can make 2 rectangles. So if I slide one triangle up to meet another, they fit together to form a rectangle. And I put the X over that triangle because we've moved it, so it's no longer there. And then we can do that with the other set of triangles. And now we have 2 rectangles that we've made out of the 4 purple triangles. And each rectangle has side lengths 2 and 4. And that tells us that the area for both of these rectangles is 8 square units. So we add those separate areas together. That's going to give us 16 square units for the shaded region. All right, our next section here is about the characteristics of parallelograms. And there's several different characteristics of parallelograms. A few that are really important to commit to memory in sixth grade is that parallelograms have 4 sides, and then they have 2 sets of parallel sides. And those parallel sides in a set are equal in length. A question type that would be used to assess whether students know or can tell the difference between a parallelogram and something that's not a parallelogram is to answer questions like this example question, where they need to either select all the parallelograms or all the non-parallelograms and then be able to defend their decision with reasons, why they chose the way they did. So, looking at these 5 figures here, the prompt wants students to select all the parallelograms. And so we kind of need to go through a mental checklist of sorts when we get to each figure and ask ourselves, does it have 4 sides? If the answer is yes, does it have 2 sets of parallel sides? And if the answer is no, then of course it's not a parallelogram. If the answer is yes, then it is a parallelogram. Okay, so starting with A, it has 4 sides. So now we want to see if it has more than 1 set of parallel sides, or even 1 set of parallel sides. So this figure here does have 1 set of parallel sides, but the other sides are definitely not parallel, because if those sides or the line that goes through that side were to go on forever, they would eventually cross. So for that reason, A is not a parallelogram. B has 4 sides, and it does have 2 sets of parallel sides. So here would be 1 set and that's the second set. So B is a parallelogram. C is also a parallelogram. It has 4 sides. It has 2 sets of parallel sides. So C is a parallelogram. D has 5 sides, not 4. And E also doesn't have 4 sides. It has 3. Below here is room for students to, or below this diagram, is space for students to write down their reasoning. And they can simply write, like for A, only one set of parallel sides. For D and E, you can write down how many sides they have and why that excludes them from being a parallelogram. All right, being able to figure out where a base and a height measurement are in a parallelogram is really important. So the parallelogram formula is the base multiplied by the height, and that base and height is going to be used to find the area of triangles. So the 4 pictures here show all the different ways that students might see a base and a height being shown in an example. The base of a parallelogram could be any side, but once a base has been chosen, the height has to connect the base to its opposite side, and it has to do so as a 90-degree straight line. So it has to be perpendicular to the base. The example to the right of the parallelogram I just drew on, the base was chosen to be that side, and in doing so, the height couldn't be drawn here because this side's not the base, and the height has to connect the base to its opposite side. And so that's why this is drawn as the height. Again, the example here has chosen the side to be the base, and so the height connects that base to the side that's opposite. This example here can be a little confusing at first for students, but if this side here is chosen to be the base, we can imagine that side extending off on this line here. And so when we connect the opposite side straight down until we reach that extension of the base, then we can call that the height. Okay, so a question that could be on the quiz to assess whether a student or students are able to determine where the height and the base are in a parallelogram would be a question like this, where you simply have to select all the examples that are correct in identifying the base and height. And so we'll go ahead and do that now. For A, because this side here has been chosen as the base, then a line that is drawn perpendicular to it is going to connect that base to the side opposite the base, meaning that this distance right here is equal to this distance, or even this distance, or this distance. So it has been labeled correctly. And I should clarify that any line that's perpendicular to the base and connects the base to the opposite side is a height. So technically there could be an infinite number of heights. But as long as it connects the base to the opposite side, and it does so at a 90-degree angle, then that's okay. That's what we're looking for. B is not labeled correctly. The base could be this, but the height is going to connect the base and the opposite side at a 90-degree angle, not at this angle here that this side is at. For C, this is the base, this is the side opposite the base. We have a line segment or a height that connects the base to the opposite side, and it is the same length as this line right here, and it's doing so here at a 90-degree angle. So this is correct. And D, for similar reasons, if this side is the base, then this height here is connecting that base to the opposite side, and that measurement there is the same measurement here. And so this is correctly labeled as the height, and the only parallelogram that was not correct is B. There we go. All right. So the last section here is about finding the area of parallelograms. And this top section here is just illustrating a couple ways that you could use to, or methods you could use to find the area of a parallelogram. So this first question here, I'm going to decompose part of the parallelogram. So I'm going to kind of slice off a little triangle there. And then I'm going to rearrange and move that triangle over. And this part isn't there anymore because we moved it over here. And so we're going to find the area of this rectangle. And it has a side length of, let's see, 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6, 7. And we'll multiply those side lengths together, and that'll give us an area of 42 square units. And another way to find the area of a parallelogram is to multiply the base by the height. So this is another question where knowing how to identify the height on a parallelogram is key. So we have a height that's perpendicular to this side here, and it connects this side to this side. So we can reasonably assume the base is that 6 and the height is 4. And when we multiply 6 by 4, we get 24. So the area of the parallelogram is 24 square units. All right, thanks for watching. Hopefully this helps. I hope it wasn't too long.